reactions, right? So asymmetric reactions mainly concern about the synthesis of chiral stereoisomers predominantly or exclusively over the other possible chiral stereoisomer. So I also explained to you that nature is the excellent asymmetric synthesis source, because all the biochemical reactions or biocatalyzed reactions produces or generates exclusively the single isomer 100%. So that's why I told you that nature is the best asymmetric synthetic source and the excellent stereoselective source. Okay, from nature we can understand and we can develop asymmetric synthesis, because asymmetric synthesis is mainly concerned to synthesize the required or the biologically active compounds or chiral stereoisomers predominantly or exclusively over the other possible chiral stereoisomers, which may not be required for us and which may not to be biologically active. Okay, so to understand more and more and to become master in asymmetric synthesis, you need to understand some terminology, some basic terminology in asymmetric synthesis. One of the terminology in asymmetric synthesis is topicity. Okay, topo is a Greek word which means a place or location. Okay, so asymmetric synthesis mainly concern about the stereo, that means the geometry of molecule. Okay, so as I said, in asymmetric synthesis the main object is to produce chiral molecules. Okay, so you know that chiral molecule is a molecule which does not have any symmetry elements. Okay, asymmetric means no symmetry at all in that molecule. Okay, like a plane of symmetry or center of symmetry, alternative axis of symmetry, all those kinds of symmetry are absent in chiral molecules. Therefore they can be considered as chiral molecules, and also those molecules are optically active, so that they can have very important biological activities, right? Topicity. Okay, topicity means topo, the place or location of different atoms or groups which are attached to in that molecule. Okay, topo is a Greek word which means place or location. Okay, so topicity means the study of stereochemical relationship between atoms, groups which are attached in a molecule. Okay, so simply, if you want to understand very easily, I can give you the best illustration to understand about topicity, right? As you know, so just recently IPL 2020 started, and many of you are watching those matches. Okay, do you observe one thing, right? So in the field, so there are about 11 fielders. They placed in different places for fielding. Okay, so if you understand about the fielders and the place of the fielders, it is very, very important, you know. Okay, captain, the team captain should understand the positions or the places or the locations of fielders in that field. Otherwise it is very dangerous for them to lose the match. Okay, so the captain a skillful captain will place fielders at a right place. Okay, so just I can illustrate like this. Okay, toposity. If you want to understand about toposity, okay, topicity, okay, the uh, the study of fielders in fielding. Okay, there are different places fielders field. Okay, similarly, in a molecule, you have substituents. Okay, you have different substituents around the molecule, around a stereo center, around the chiral center. Okay, so their positions, their places, their locations, uh, we have to understand. Then only we can fully understand about asymmetric synthesis. Okay, so topo means place or location. So toposity, the definition for toposity, okay, the study of stereochemical relationship between atoms or groups in a molecule which they are attached, okay, or the study of spatial orientation, of subunits in a molecule. Subunits means atoms or groups, okay, in a molecule. Okay, so I gave you one illustration or one example. Okay, X and Y, hydrogen and hydrogen. Okay, topicity means these atoms or groups attached in that molecule. Okay, so we will find out the relationship between atoms or groups in a molecule, in a stereoisomer. Okay, in a chiral stereoisomer, in a stereoisomer. Okay, so because if you understand about the topicity of that molecule, then it is easy for you to understand about asymmetric synthesis. Okay, so the definition you must understand clearly. It is very easy. Topicity is nothing but the study of stereochemical relationship between atoms, groups in a molecule which they are attached. Okay, here A, B, X, Y, H, H, these are atoms or groups which are attached in that molecule or in the chiral centers. Okay, or in the stereo centers, right? So topicity, that means, so we are going to find out the relationship between these two hydrogens, for example. Okay, these two hydrogens, stereochemical relationship we'll find out or we'll study in topicity. So that is topicity. Topicity, the study of stereochemical relationship between atoms, groups in a molecule which they are attached, or the study of spatial orientation of subunits. Subunits are nothing but atoms or groups in that molecule which they attached. Okay, so that is the definition of topicity. Okay, so let me give you another terminology definition. Homomorphic unit. Homomorphic unit. Homomorphic unit. Okay. Homomorphic unit. That means the groups, the atoms are groups. The atoms are groups which are in isolation, looks the same or mirror superimposable mirror images of each other in a molecule is said to be homomorphic unit. Homomorphic unit. Okay, so homomorphic unit, the definition for homomorphic unit: the atoms are groups which are in isolation, looks the same or superimposable mirror images of each other in a molecule, okay, is said to be homomorphic unit. Okay. So when if I draw a molecule, then you will understand clearly. First of all, unit means it may be ligand, or it may be phase. Okay, both can be considered as unit. Okay, ligand or phase. Ligand means atoms are groups. Phases mean the plane above or below plane. Okay, so unit can be considered as ligand or phase. Okay, ligands may be atoms or groups. Phase means the plane may be above or below the plane. Okay, so homomorphic unit, the atoms groups which are in isolation looks same or superimposable mirror images of each other in a molecule is said to be homomorphic unit. I'll give you I'll draw the structure. Okay, A, B, C, D. Okay, so in this center atom, 4 groups attached which are in isolation. Isolation means separation. Looks the same. HA, HC, HB, HD. All hydrogen atoms are same. And superimposable mirror images of each other in a molecule. So in methane molecule, 4 hydrogen atoms are same and in separation, in isolation, and also superimposable mirror images of each other. So they can be considered as homomorphic unit. I'll give you another example. That's the acetone. Okay. In acetone, these 2 groups, CH3 and CH3, they are homomorphic units because in isolation they are same, and also they are superimposable mirror images to each other. Okay, and I'll give you one more example. This is the hydrogen and the OH, hydrogen, COOH. Okay, in this both the hydroxyl groups and the hydrogen groups and COOH groups, they are homomorphic units. They are homomorphic units because in isolation they looks the same functional groups, and also the superimposable mirror images of each other. So therefore they can be considered as homomorphic unit. Therefore they can be considered as homomorphic unit. Okay, so this terminology you need to understand. Homomorphic unit may be considered as ligand or phase. Ligand can be considered as atoms or groups. Phase or above or below plane. Okay, the definition for homomorphic unit: the atoms groups which are in isolation looks the same or superimposable mirror images of each other in a molecule is said to be homomorphic unit. So these are the examples: methane and acetone and this dicarboxylic acid. Okay, so in that these 4 hydrogens are homomorphic units, in these 2 CH3 groups are homomorphic units, and these 2 hydroxyl groups and these 2 hydrogen groups and these 2 carboxylic groups are homomorphic units because they are similar, because they are same. Next, homomorphic units can be classified into different types. Okay, homomorphic units can be homotopic units, or heterotopic units. They can be classified like that. Further, homotopic units can be classified into homotopic ligand and homotopic phase. Okay, heterotopic unit can be classified as stereoheterotopic unit, and another one structural heterotopic unit. Okay, homomorphic unit can be broadly classified into homotopic unit and heterotopic unit. Homotopic unit further classified or divided into homotopic ligand and homotopic phase, and heterotopic unit further classified as stereoheterotopic unit and structural heterotopic unit. Okay, so there is a difference between stereoheterotopic unit and structural heterotopic unit. In structural heterotopic unit, you will consider about the connectivity of atoms or groups. Okay, but whereas in stereoheterotopic unit, you will consider about the configuration of the molecule. Okay, stereoheterotopic unit further classified into enantiotopic unit and diastereotopic unit. Okay, stereoheterotopic unit can be further classified enantiotopic unit and diastereotopic unit. So enantiotopic unit, again you will you can understand about enantiotopic ligand and enantiotopic phase. Similarly, diastereotopic unit also further divided as diastereotopic ligand and diastereotopic phase. This is again can be further simplified as diastereotopic ligand and diastereotopic phase. Further simplified, or further you will understand clearly. Okay, and structural heterotopic unit also further simplified as structural heterotopic ligand, structural heterotopic phase. Okay, so finally you are going to study about ligand and phase. Okay, so as I said initially, unit means it may be ligand or it may be phase. Okay, different phase. Okay, ligand may be considered as atoms or groups which are attached in that molecule, and phase also the different planes above or below. Okay, or towards the viewer or away from the viewer, those are the planes. Phase can be considered like that. Okay, so this is the best classification, and you can understand all these simplification terminology. Homomorphic unit can be classified into homotopic unit and heterotopic unit. So these are the terminology you are going to define, and as well as I am going to give you some examples and explanation about them. Okay, so that asymmetric synthesis will be easy for you to understand if you understand this terminology. Okay, a homotopic unit further simplified as homotopic ligand or homotopic phase, and a heterotopic unit further simplified as stereoheterotopic unit or structural heterotopic unit. Stereoheterotopic unit further classified as enantiotopic unit and diastereotopic unit. Enantiotopic unit may be ligand or phase. Diastereotopic unit can be considered as ligand and phase. And structural heterotopic unit also, structural heterotopic unit ligand and structural heterotopic unit structural heterotopic phase. Okay, so this is the classification you need to remember. So all these terms we are going to define and explain with examples, some examples. Okay, so I already gave you definition for homomorphic unit. Okay, so homomorphic unit, the atoms or groups in isolation looks the same, and superimposable mirror images of each other in that molecule. Okay, so that is about homomorphic unit. First let us try to define homotopic unit. Homotopic unit or homotopic ligand and phase. Unit means ligand or phase. Hmm? Homotopic unit or phase. So first let me define you about homotopic unit. The atoms groups appear to be identical or equivalent are called homotopic units. The atoms are groups, that means ligands, which appear to be identical or equivalent is called homotopic units or homotopic ligands. Okay, so the atoms are groups which appear to be identical or equivalent in a molecule is said to be is called homotopic unit. Okay, I'll give example to understand about that. HA and HB. Okay, so this is otherwise you can simply without dyeing just ethylene. Okay, and these HA and HB are identical in that molecule and equivalent. Okay, therefore they can be considered as homotopic ligands. Okay, so here the atoms are groups which appear to be identical or equivalent. In this alkene, HA and HB, both the atoms are identical because both the other substitutions are chlorines. Therefore, the environment is same. Okay, and you cannot distinguish this hydrogen separately. They are identical and they are equivalent in NMR also. Okay, so they will give equivalent peaks. Okay, so therefore these HA and HB, both the atoms are considered homotopic ligands. I'll give you another example for homotopic ligands. So malonic acid, COH and COH, in this these two atoms are identical and equivalent. Therefore HA and HB are identical and equivalent. Therefore they are homotopic ligands. Okay, homotopic means the atoms groups which appear to be identical or equivalent in a molecule is called homotopic ligand. So I gave you two examples. One is alkene, dichloroethylene, right? dichloroethylene, right? In that two hydrogens, Ha and Hp, so they are identical and equivalent, therefore they can be considered as homotopic ligands. And in this malonic acid, okay, Ha and Hb are identical and equivalent, therefore they are also considered as homotopic ligands. Okay, so I'll give you some more examples to understand about homotopic ligands. So to find out homotopic ligands, okay, there are two criterias. By using those two criterias, you can identify or find out whether they are equivalent or not, whether they are homotopic or not. Okay, so two criterias two criteria are used to find out, to identify or to find out, to identify whether the given atoms or groups are identical or not, identical or equivalent or not, equivalent or not. Okay, so there are two criterias which can be used to find out or to identify whether the given structure, atoms or groups identical or equivalent or homotopic or not. Okay, what are those two criterias? One criteria we can understand is symmetry criteria. Symmetry criteria. The other one is substitution or addition criteria. Substitution or addition criteria. Addition criteria. These are the two criteria used to find out whether they are homotopic or not, whether they are identical or equivalent or not. Okay, so we can explain about symmetry criteria. What is symmetry criteria? How we can find out, how we can identify whether they are homotopic or not. And I am going to explain you about the second criteria also, substitution or addition criteria. How we are going to find out or identify whether they are homotopic units or not in a given molecule. Okay. First, let us try to understand about symmetry criteria. Symmetry criteria. By using this criteria, how we can identify, how we can find out whether the given atoms or groups are homotopic or not in a molecule. Okay, so symmetry criteria means the atoms are groups, the atoms are groups which are interchangeable or interconvertible, interchangeable and interconvertible with CN symmetry axis. CN symmetry axis is called homotopic ligands. Homotopic ligands. Okay. So on the basis of symmetry criteria, we can define homotopic ligand. How we are going to identify or find out? The atoms groups which are interchangeable. That means if two atoms or groups interchangeable or interconvertible with CN symmetry axis. With what? CN symmetry axis. It may be C2 or C3 like that. Okay, axis is called homotopic ligands. It's called homotopic ligands. So I'll give examples for that. So this is the formaldehyde. So this molecule has symmetry, okay, C2 symmetry. So if you rotate with this axis, the HB will come this side. So both the HA and HB are interchangeable or interconvertible. Interchangeable or interconvertible. Interconvertible with C2 axis of symmetry. C2 symmetry axis. Okay, if you rotate 180 degrees, okay, so these HB will come this side and this HA will go there. So they are interchangeable, they are interconvertible with each other with C2 axis of symmetry. Therefore, these HA and HB are homotopic ligands. These HA and HB ligands or atoms are homotopic ligands. So by this way you can understand or you can find out homotopic ligands. Suppose ammonia molecule, you take ammonia molecule, it's a pyramidal shape, okay. So is there any symmetry element in this symmetry axis? Okay, rotational axis is there, C3. These three hydrogens are interchangeable. These three hydrogens are interchangeable and interconvertible. Therefore, they can be considered as homotopic ligands. They can consider as homotopic ligands. Because of this C3 symmetry axis, if you rotate that molecule, so they can be interchangeable and interconvertible without any difference. Okay, so therefore these HA, HB and HC are homotopic ligands. Homotopic ligands. How we find out? Due to symmetry criteria. Okay, so in this C3 axis of symmetry is there, and if you rotate the molecule, these three hydrogens or these three groups interchangeable with each other without any difference. Therefore, they are homotopic. Homotopic means no difference. Okay, similar or same. And I'll give more and more examples on this to find out symmetry criteria. Okay, uh, if you take this water molecule, okay, if you rotate with this axis, with this symmetry axis, so these two hydrogens are similar, same, without any difference. They can be interchangeable and interconvertible. Therefore, these two hydrogen groups are homotopic. These two groups are homotopic. And if you take a methane molecule which has tetrahedral okay, HA, HB, HC, HD. So it has also C3 axis through this axis. Okay, C3 axis. And all these hydrogens are interchangeable, HA, HB, and HC, and HD. All the hydrogens in methane molecule are able to interchangeable and interconvertible without any difference. Therefore, these groups or atoms are considered as homotopic. Okay. So I'll give another example. Suppose this dibromo compound HB. What about these two atoms or groups, HA and HB? Are they homotopic or not? How we can find out? Okay, so it is the CN axis. Okay, that means C2 axis, symmetry axis. If you rotate through this axis, both the HA and HB are interchangeable or interconvertible. Therefore, they can be homotopic. And even these two bromine atoms also interchangeable and interconvertible with this C2 axis of symmetry. Therefore, HA and HB and also two bromines are homotopic units. HA and HB and two bromine atoms are homotopic because these atoms or groups interchangeable and interconvertible through CN axis of symmetry. Therefore, they can be considered as homotopic ligands. So this is the way, by using symmetry criteria, you can identify, or you can identify homotopic, whether they are homotopic or not. Okay, and so what about this cyclopropane, substituted cyclopropane, HA and Br, HB and Br. So it has also axis, CN axis. If you rotate this one, are they interchangeable or interconvertible in this case? So I'll give you two molecules. HA and Br, Br and HB. Suppose these two molecules. So here if you rotate this one, actually these hydrogens bromines are in three-dimensional spatial arrangement. So for convenience I wrote like this, but these HA and HB and Br, they are not homotopic because they are not interconvertible or interchangeable with each other. Okay, so if you rotate the this side bromine will go this side, and this HB will come this side, this bromine will go, and like that. Okay, they will not be interchangeable or interconvertible, but whereas here they are interchangeable and interconvertible. If you rotate this one with the CN axis, this HA can be replaced with HB, and HA will come this side, this bromine will come this side, and this bromine go there. So they can be interchangeable or interconvertible. So therefore, so this HA and HB and Br is homotopic, whereas here HA, HB, Br and Br not homotopic, okay. So because of this symmetry criteria, CN axis of symmetry, we can be able to find out, or we can able to identify whether they are homotopic or not. Okay, so that is the symmetry criteria, and I will give some more examples on this. So diene, HB and HC and HD. So what about these atoms or groups? Are they homotopic or not? So this is the symmetry criteria. Axis, CN axis. So if you rotate that, they can be replaceable, or if you rotate like this, so HA and HB and HC, HD, they are homotopic. They are interchangeable and interconvertible, therefore they are homotopic units, okay, or ligands. CN axis of symmetry. So I'll give two more examples. HA, HB, HC, HD, HD. Okay, so here is the CN axis of symmetry. If you rotate this CN axis of symmetry, the HD will come this side, HC will go there, HA will come this side, HB will come this side. They are similar, they are interchangeable, interconvertible, therefore they can be considered as homotopic ligands. HA and HB and HC and HD, they are homotopic units are homotopic ligands. That we can understand. Suppose this tartaric acid these two hydroxyl groups are homotopic or not? These two hydrogens are homotopic or not? These two carboxylic acids are homotopic or not? Yes, they are homotopic. Okay. So if you have the CN axis of symmetry like this, okay, so they can be interconvertible, they can be interchangeable. Therefore, hydrogens and hydroxyl groups are homotopic, COH and COH. These are homotopic units. Homotopic units. Homotopic units, okay? So I hope with all these examples, so you will be able to identify whether they are homotopic or not by using symmetry criteria, okay? So the second one is what is the other criteria we can use? Substitution or addition criteria. The second one is substitution or addition criteria. With the help of this criteria also we can identify whether they are homotopic or not, okay, whether they are homotopic or not. The atoms are groups that are interchangeable or interconvertible with CN axis of symmetry are known as homotopic ligands. Substitution criteria, okay. Substitution or addition criteria. The atoms are groups hypothetically substituted with new reagent or new atom or group, that produces same products are said to be homotopic ligands, okay. So this is the substitution criteria, okay. The atoms or groups in a reactant, in a molecule starting material, hypothetically substituted with new atom or groups that produces same products. If they produce same products, are said to be homotopic ligands, okay, are said to be homotopic ligands. Simple example. So H1, H2 and H3 and H4. This is the methane molecule. If you replace H1 with chlorine, you will get CH3Cl. If you replace H2 with chlorine, you will get CH3Cl. If you replace H3 with Cl, you will get CH3Cl. If you replace H4 with Cl, you will get CH3Cl. Okay? Therefore, H1, H2, H3, H4 are homotopic ligands, are homotopic atoms, because the atoms groups hypothetically substituted with new atomic group that produces same products. So here in this hypothetical reaction, you will get same products by replacing four different the four hydrogen atoms, which are not different, they are same. Okay, so you will get same product if you replace this H1, or if you replace this H2 with Cl, or if you replace H3 with Cl, if you replace H4 with Cl, you will get same products in four cases. Therefore, these hydrogen atoms are homotopic ligands. Therefore, these four hydrogen atoms are homotopic ligands. Okay, so that is the definition. By the substitution criteria, we can identify whether they are homotopic or not. Okay, the atoms groups hypothetically substituted with new atomic groups that produces same products are said to be homotopic ligands. Okay, it is very simple. And suppose you take benzene atom, one, two, three, four, five, 6. If you replace hydrogen with chlorine, in all the 6 cases you will get chlorobenzene, same compound. Okay, if you replace any of this hydrogen with new atom chlorine, and the given the yielded product is same in all the 6 cases. Okay, therefore these hydrogens or atoms are same, produces same product by substitution criteria with Cl. Therefore, they can be considered as homotopic ligands. They can be considered as homotopic ligands. Okay, dear students, I hope the terminology in asymmetric synthesis, it is very easy to understand if you go through them, if you go through my class. Okay, I also provide notes on this class. Okay, so try to learn this terminology in asymmetric synthesis. I'll continue in the next class about heterotopic units. Okay, so today you learned that what is topicity, the definition for topicity. Okay, and basic terminology terms like homomorphic unit, you learned about the definition and as well as examples about homomorphic unit. Homomorphic unit can be mainly divided into homotopic unit and heterotopic unit. Okay, homotopic unit, you learned about homotopic unit. In homotopic unit may be considered as ligand and phase. Okay, so today you learned about homotopic ligands. So how to find out, what are the criteria we can use to find out homotopic ligands? Okay, so there are 2 criteria which are used to find out or identify whether they are homotopic or not. Okay, so what are those 2 criteria? One is symmetry criteria, the another one is substitution or addition criteria. So I gave you enough number of examples to understand about those terminologies. So try to concentrate and learn about those terminology in asymmetric synthesis. Thank you. Bye.